Good afternoon and welcome to the Professorial Inaugural Lecture to be delivered by Professor James Ransford, Dankwah, the Vice Dean of the Faculty of Mining and Minerals Technology and the Head of the Department of Minerals Engineering. Shall we please rise to receive the Vice Chancellor's procession?
Shall we pray? God of mercy and of grace, we thank you for the gift of this day. We express our appreciation to you for the vision and the mission of this noble university and for our country, Ghana. We thank you for the opportunity to conduct this inaugural lecture. We also want to thank you for the life of our special speaker, Professor James Ransford Dankwah, who will be professing today on the topic Waste Plastics, a Modern-Day Resource Paradox, leveraging its positive attributes for an environmentally sustainable metals production. We are grateful to you again for the traveling message you have granted to all dignitaries, alumni present, students, the press, and all those who have traveled from far and near to grace this function. We commit into your gracious hands, O God, the proceedings of this function to a successful end. Remind us, O Lord, of the guiding principles by which the business of this university has always been conducted through the pursuit of knowledge, truth, and excellence. This is our humble prayer, O God, as we assemble for this inaugural lecture. Amen.
Please, you may resume your seats. Good afternoon, ladies and gentlemen. It is my pleasure to welcome you all to the inaugural lecture of Professor James Ransford Dankwah, a professor of metallurgical and materials engineering. He is an immediate past dean of the Faculty of Integrated Management Science and the current head of the Department of Minerals Engineering of this university. This marks the 10th inaugural lecture of the University of Mines and Technology. A professorial inaugural lecture is a significant milestone in any academic's career, recognizing their promotion to professor. It provides an opportunity for the professor to present their research findings, contributions to their field, and their overall scholarly journey before an audience of members of the university community and the general public. We are gathered here this afternoon to listen to Professor James Ransford Dankwah about his research breakthrough in the field of metallurgical and materials engineering. This said, it is now my honor to introduce the chairman of today's inaugural lecture. He is a distinguished and internationally acclaimed scholar and administrator who has provided dedicated service for many years in various universities, both locally and internationally. He has served as a researcher, investigator, or consultant on several international and local projects funded by the British Council, European Union, United Nations, World Bank, Ghana, and several mining and allied companies. He has won several notable awards, including the Lifetime Gold Legend Award by Forbes Monaco. Ladies and gentlemen, the chairman for this memorable occasion is the Vice Chancellor of this university, Professor Richard Kwesi Amankwah. Shall we give him a standing ovation?
Please be seated. Please be seated. Thank you very much. Normally, when I hear this standing ovation thing, I normally cringe in, but thank you for doing that. Today is a very great day as far as the university is concerned, and we are happy to have all of you here. Let me acknowledge the inaugural professor, Professor J.R. Dankwah, principal officers of this university, deans, heads of departments and units, Nananum, the former registrar, Mr. Bedai, who I see, and Dr. Tufo Kwati, who makes time for every university program that we organize, captains of industry, distinguished ladies and gentlemen, and our friends from the media. We are happy today because one of our own, a very distinguished professor, is here to give his inaugural address. As we are all aware, when somebody becomes a full university professor, he engages the community and the university, takes us through his research, and at the end of the day, professes. That is what professors do. They profess. And today we have a very learned gentleman amongst us to profess. James Ransford Dankwah is a professor. Can you please get up, inaugural professor? He is the man. And I will read a short profile about him. James Ransford Dankwah is a professor of metallurgical and materials engineering at the University of Mines and Technology, that is UMaT. He is currently the Vice Dean of the Faculty of Mining and Minerals Technology and also the head of Department of Minerals Engineering. He obtained his PhD in Material Science and Engineering from the School of Material Science and Engineering, University of New South Wales in Australia, and his MSc in Process Metallurgy from the Norwegian University of Science and Technology, Trondheim, Norway. He had his BSc in Metallurgical Engineering from the Kwame Nkrumah University of Science and Technology in Kumasi. And indeed, that is where I met J.R. Dankwah. I went to first year in 1985, and he came in 1986. So he was 1 year my junior, but we had a very strong association. And when I started my master's, he was a teaching assistant, and we have stayed together since. I know him very well. James Ransford Dankwah has current research areas, which include bauxite processing, iron and steel technologies, high-temperature metallurgical and materials processes, corrosion and corrosion control, electrowinning, electro-refining and electroplating, utilization of end-of-life polymers as reductants in metal extraction processes, the production of diesel from end-of-life polymers, lubricants, and also from end-of-life polymers, extractive metallurgy of aluminum, gold, copper, nickel, bauxite, and zinc. This has resulted in over 100 journal, conference, and technical publications. Professor J.R. Dankwah is a vibrant researcher and an innovator across several scientific and technological disciplines. And he is the co-founder of the African Center for Sustainable Materials and Technology. Professor J.R. Dankwah has consulted widely for several companies, both locally and internationally, among which are Gold Recovery Company, Ghana Limited, Sevaco PPS Ghana, Makeza Group, Sierra Leone, Steelfort, and PVT Limited, Sierra Leone. He has so far supported students, 17 masters and 164 BSc and diploma students to completion. He is currently supervising 35 undergraduate students, 19 master students, and 3 PhD candidates. Professor Dankwah is an external examiner and assessor at the Department of Materials Engineering and Chemical Engineering at KNUST. He is also a fellow of the West African Institute of Mining, Metallurgy, and Petroleum. Ladies and gentlemen, I present to you your inaugural professor.
Thank you very much, Vice Chancellor, Professor Richard Kosi Amankwah, for this opportunity and then the honor done me. Vice Chancellor, Professor Richard K. Amankwah, VCs of sister universities here present. The Pro-Vice Chancellor, Professor Mrs. Grace Ufuri Sapon Akufu, and Pro-VCs of sister universities. The Registrar, Mr. Matthew K. Okra, and Registrar of sister universities. The Finance Officer, Mr. Jonathan Seko, the University Librarian, Dr. Mrs. Ajua Yaboa. Hope I got your name right. If I didn't, please forgive me. Former Registrar, Mr. Ebenezer Kwakubidai. Sir, I am grateful to see you here today. Thank you very much. It means a lot to me. The Dean, Faculty of Mining and Minerals Technology, Professor William Kwame Boa. My Dean, thank you very much. Deans of faculties and schools here present and online, all past inaugural lecturers here present, all professors of the University of Mines and Technology, UMaT, the very Reverend Samuel Kofi Amo, I know you are here. Thank you very much for making it to Dankwah. Superintendent Minister, Methodist Church, Apiga Circuit. Apostle Samuel Otuapia was supposed to have been here today. Unfortunately, something happened. He is an apostle of the Church of Pentecost, Ahafugo, so where my late father comes from. And all clergy here present. Nana Abra Boatin. Nana, is it the first? I think it is the first. Chief of Nyinahine Ashanti. Nana, I am very honored to have you here. Ladies and gentlemen, before I continue, Nana Abra Boatin happens to be my teacher at the senior high school. Nana taught me English and English literature. Nana, I am your product. This is the work that you did several years ago, and today you see me here, stand before you as a professor of metallurgical and materials engineering at the great University of Mines and Technology, Dankwah. Thank you very much. Bafo Ourai and Chikokroko II, Krontihini of Achim Apiga, my hometown. Nana, Yamawakwaba. Nana, Yamawakwaba. Nana Abna Abwajiwa Asantiwa, the all beautiful Queen Mother of achim apiga. Nana imawapaba. Nana Abna Kunajua II, Paramount Queen of Wasa Fiase traditional area. If you are here, Nana Akwaba. Nana Nkebua Pra the 4th, Divisional Chief, Pristia Himan traditional area. If you are here, Nana Akwaba. Nana Kwasi Blay, Apinto Divisional Council, Nana Shawaha Mimwakwaba. Nana Adakwa Bidia Ko the 3rd, Jasihine Apinto Divisional Council. If you are here, Nana, you are welcome. Akwaba. Nana Dupenyin Apinto Tufuhine. Nana Kojo Mina the 2nd Chief, Tebre Bay and all Nananum here present. The General Manager, Gold Falls Ghana Limited, Dr. Mrs. Catherine Kupo Quito. If you are here, you are welcome, and thank you very much for making it. Members of convocation here present, senior engineer staff here present, students of UMaT, members of the Methodist Church here present, members, the Christian fraternity here present, my classmates. Today is a great occasion. I have my teacher over here, but I have one of my classmates also over here. Warrant Officer Joseph Amon, please, thank you very much. You can stand and let them see. I went to secondary school at the age of 13. And I remember the first day I was told to go home and then continue to suck breast because I was too young. But we had those who were there to protect us. And warrant officer, no wonder he became a military man. He was one of the guys who would always protect us. Thank you very much, W. I appreciate it. I have my mates from Ghana Senior High Technical School here. One of them is our own Professor Anthony Simmons, who did his inaugural lecture, who handed his baton to me. We were in GSTS together. If there are any members of the Muslim community here present, you are welcome. Distinguished guests, ladies and gentlemen, I deem it a huge privilege to stand before you this evening to share with you the research that I have done for the past 24 years at the University of Mines and Technology. Before I continue and then delve into the actual research, because I think my profile has already been read by the VC, and I don't want to go there to bore you too much. But before that, let me take this opportunity, just about a minute, to say a very big thank you to my wife, and then two of my children here. So Mrs. Jocelyn Dankwah, please, will you please stand up for just a minute? Thank you very much. You are like a stone and a rock. Trust me, over the years, there have been several instances that I nearly gave up. But if you see me today, it is because on earth, as a spiritually, our Father in heaven always takes care of us. But there is a rock. And I have no shame in saying that my earthly rock is my wife, Mrs. Jocelyn Dankwah. Thank you very much for your love. It got to a point, you were the only person who could see the good in me. And today, that goodness is shown me over here by the grace of God. Thank you very much. Then to two of my kids, my firstborn, Jessica Dankwah, who is an engineer at the at Goldfields Ghana Limited, the M-AMRS, and also currently a PhD candidate at the University of Mines and Technology. Jessica, thank you very much. I love you. My second born, Dr. James B. Dankwah, was also a student here. He's currently in Australia after obtaining his PhD, so he's currently applying his trade over there. And then lastly, my last born, Dr. Jason Reginald Dankwah, please. Let's see. He is just graduated from KNUST School of Medical Sciences, so very soon he will start. I hope that, unfortunately, when I get sick, he cannot take care of me because I think it's unethical. But I don't know, I may be wrong, but thank you very much. And so now, I will move straight away to the purpose of this lecture. I think the reasons for doing an inaugural lecture has already been said by our distinguished registrar. So I'll move straight away to my research. I need to share the research with you. Before I move, Ghana and the global community is currently faced with a huge problem that if we are not able to tackle this issue, our very existence, I see it as threatened. I'm not talking about Galamsey. Galamsey is also there, which probably is restricted to Ghana and a few other African countries. I am talking about a very important resource. I'm sure as we sit here, we all can see our Baltic water bottle over here. The plastics is like the proverbial acantrophy anomaly. Say, I may come over too much, I am offending me. But when it gets to a point, I may have to come and then maybe mix my lecture with the local dialect. Plastic is like the proverbial acantrophy anomaly. And if you take a look at the topic of my inaugural lecture, waste plastics, a modern day resource paradox, leveraging its positive attributes for an environmentally sustainable metals production. Yeah, plastics has a lot of benefits. Until the advent of plastics, those of us who came from the villages, you saw that we used to have our food in several leaves, aroma and the like, a lot of them. Those things look hygienic. But from the point of view of convenience, I think they also had their shortcomings. So plastics made its way somewhere around 1950. And since then, there has been an explosion in the production of plastics. Because of the convenience of using plastics, it has gotten to a stage where, because of, once again, convenience, we use most of these plastics, and then after using them once, we dump them. But when we dump them, where do they go? It has been said that by the year 2050, we're going to get more fish, more plastics in the ocean than we have fish. Maminka way ewo chi kasam said the buyer in Naibehu said the plastics are very dangerous. And I may say it is a acantrophy anomaly. Ewo ni positives and ni negatives. Yes, say according to UN report, almost say year by the year 2050, you caught a pumu and now you caught in the water body in Ghana, say a fishing. you bring out more plastics in the ocean than we have fish. And I think today, if you can bear me out, those who stay along the coastal regions of Ghana, our fishermen, whenever they go for fishing, you cast your net, and then what do you get? You get a lot of plastics waste. So this is a very dangerous thing that we need to confront head on. And that is why my polymer reduction technology will be part, or will be the central theme for my research today. In the next few minutes, I'm going to bore you more with a bit of some equations. Please forgive me, I wish I could do something about it. Those who remember a bit of chemistry, traditionally, the industrial way of producing metals, especially in the iron and steelmaking technology, is to use a material known as metallurgical coke. Because of all the iron, metals, iron, and this iron, very good, we change it into steel. Okay? Traditionally, your material bakwa is your friend metallurgical coke. Now, any country beer and the world say material. So for this reason, if you find yourself in a region where you do not have some of these materials, it means that you need to sit down and then think about how you can also process your metals. Countries like Brazil, they do not have coal to turn into metallurgical coke. So what they do is that they have a tree species that they call eucalyptus. I wish we had some over here in Ghana. It's a very fast-thriving tree. Unfortunately, here it also places a lot of threat on our water bodies because it's able to suck a lot of water. But that is what they use in Brazil. They cut the eucalyptus plant, turn it into charcoal, and then they use charcoal as a source of carbon to produce their metal. If you go to the Gulf region, they have a lot of natural gas. So they use natural gas to produce their steel, their iron and steel. And then there are other countries where you need to balance between the two, you put them together, and then which of them is cheaper, you go for it. In 2019, government of Ghana came out with two important industries, the GIADEC and then the GISDEC. Now, the GISDEC was created for job creation and industrialization. Now, their mandate is to oversee all the iron ores in Ghana, create jobs from them, and then also for industrialization. I'm saying, we invest in national service 1 year, and most of them will go into retirement because there are no jobs. And that idea in 2019 was a noble one to help us create jobs for the teaming youth in Ghana. We have a lot of iron ores, I'll be mentioning them as I move on, but we do not have metallurgical coke. And if you understand the chemistry of metals production, you need what is known as a reducing agent. And this reducing agent is normally taken from carbon, which is the best in terms of availability. These days we're moving away because we want to cut down on a carbon footprint, so we move on to other materials like hydrogen and so on and so forth. The good thing about the plastics, the positive attributes of the plastics, is that plastics contain the carbon and then the hydrogen that are needed for reduction to produce our metals. And so you ask yourself, in Ghana, government want to set up a metals production industry in the iron and steels making sector, but we do not have metallurgical coke or coal. Are we going to go to our forests already? We're suffering from deforestation to cut down trees? I think we all know the answer. The answer is no. So then that was one of the reasons why we started thinking about how to solve this issue, and therefore we came out with our polymer reduction technology. Plastics contain carbon and hydrogen. And this is the mechanism that I have over here. I'm not going to bore you too much. If you see that we have the last stage of iron oxide reduction, which normally is the rate determining step, reacting with hydrogen to form water. We have the water gas shift reaction, and then two very important reactions, the water gas reaction and then the Boudouard reaction, and also you need to have your carbon dissolving in your steel. When plastics react with metal oxides, because the plastics contain both carbon and hydrogen, both the carbon and hydrogen will take part in the reduction process. For this reason, we have an avalanche of reductants available within the reaction system, and therefore reaction is able to go on at a very fast pace. I'll be sharing some of the work that we have done, and we compare the use of plastic waste to the traditional metallurgical coke. And then you notice that because of the large amounts of reducing agents, when you use plastics, you have a lot of advantages. This is the equation based on which we did all our reaction. So let's not worry you too much, but those who understand mass balances will understand everything is here. Normally, I have attended conferences and they ask me, but the equations that you use in deriving, in getting your rate of reaction or your extent of reaction, you're doing something at 1,600 degrees Celsius. How are you able to use the universal gas equation to come about with your equation? Now, if you want to know, the answer today is that in accordance with the kinetic molecular theory of matter, gases appear to behave more ideal at high temperatures and low pressures. Now, for this reason, whenever you go into the iron making scenario, we have temperatures in excess of 1,000 degrees Celsius. And then most of these processes are exposed to the environment. So the two conditions of high temperature and then low pressure are met. So I can have every gas that leaves the reaction system and use it as a basis for determining the progress of the reaction. That is the only way you can do it, because physically you cannot jump into the furnace at 1,600 degrees Celsius. The human body evaporates at 500 degrees Celsius. To 1,600 degrees Celsius, you can't do that. So we use simple equations, and these equations are valid from the scientific point of view. All I need is to understand my PV is equal to nRT, and I'm able to use that to engineer my equations, and then I come out with a design from this, using these mass balances. So I have a mass balance for oxygen, because in reduction, I take oxygen from the oxide, and I produce my metal. You also need to have an idea about the carbon that you consume, because these days you say we're cutting down our carbon footprint. So the equation also takes into account our carbon consumption, our hydrogen consumption, oxygen consumption from the oxide. And when you put all these pressures together, you add them together because the system is exposed to the environment. They sum up to give you a total pressure of 1 atmosphere. And with that, you're able to do whatever you want to do. So I'm able to calculate my extent of reduction and then my rate of reduction easily. And when we compared, there was virtually no difference in what you obtained and then if you were to measure it raw. I have some metal oxides over here. If you want to produce one of these metals at high temperatures, you probably come across these metals. If you use thermodynamics, you are able to know the minimum temperature that is required by carbon and carbon monoxide to reduce these oxides, as stated. Now, to applications. I will take you through a few of the plastics that we have used. In fact, all of them are able to do the same work. And the plastics na abuafa yenso na enunti ema eniema enko yino na plastics ni na kogu waste ayino isumu no our seed. I am going to go through some of the work that we have done. This is takeaway food containers. Takeaway food containers. When we get there, one of the very common items is your takeaway food container. We put our food in, we eat our food, and then we discard it. As to what happened to it, it's nobody's business. But we're able to use this takeaway containers to do our work. Prof. Chairman, now a bit about the statistics of plastic waste. Only 9% of waste plastics are recycled. Plastics 100 be produced by 9 per any recycled. The rest are either landfilled or dumped illegally. In Ghana, they say nowadays ours is higher than the global average because if you go to Accra, they are doing a lot of recycling. So probably higher than 9%, but it's still low. Now, because of the popularity of takeaway food containers, a lot of them are thrown into the atmosphere. Unlike plastics like high-density polyethylene, waste polystyrene is not recycled anywhere in across the globe. People will run away from them because they don't want to have anything to do with it. This is a bit about some facts about waste polystyrene, our takeaway food containers. So we did this work, then experimentally we put some certain things together. We formed some blends. We did not want to take away the conventional material completely, so we did some blending. These are some of the properties of the conventional material and the polystyrene that we use. If you take a look at it, you see that for carbon, coke has only 78.7 as opposed to 92.26 from the polystyrene. So carbon is there. One advantage of using waste plastics is that you produce only a limited amount of ash, which is not good in iron making process. So it has an advantage over there. We tried doing this work using an electric arc furnace slag. That is the property. Then we talk about sample preparation. One major difficulty about using plastics is to how to get them in the form where you can use it in, you can have it to serve its purpose as a reducing agent. 3 ways for doing that. You can use what we call, use this machine, place the plastics in, it cuts them into pieces, it crushes and pulverizes them, and then sieve them, and then you can use the sieve component as your reducing agent. In Ghana, one other thing too is that you can also put these plastics in liquid nitrogen. That will cause it to become brittle, and then you can crush. When we did this, we were able to crush, and then first we did some thermal decomposition studies, followed by our reduction studies in a horizontal tube furnace. Prof. Chair, these are some of the results that we obtained. If you take a look at it, you see that at high temperatures, your polymer, whether it is polystyrene, HDP, or whatever, will turn into predominantly carbon monoxide, methane, and then a little bit of carbon dioxide. We wanted to see whether hydrogen is present, and we did a gas chromatographic analyzer. You can see heaps of hydrogen being produced. These are the RI gas reduction analysis for the reduction process. And then these are the extent of reduction. If you take a critical look at this, okay, you see that metallurgical coke is the last one, the lower to the right-hand corner. If you want to have an idea about efficiency of the process, anywhere any of the lines cuts the horizontal axis at the top, you drop a vertical line, you can get the time for complete reduction. Within 10 minutes, metallurgical coke was doing only about 45% reduction. PS70, which is a blend of the polystyrene, had already gone to completion, and the rest were at a very high extent of reduction. That is what we got after the reduction process. This is EAF slag, so you don't expect to, but the metals are there. You can see those spheres over there. And then when we characterize, we saw that we produce predominantly iron at the peaks 45, 65, and 82 degrees Celsius for the 2 theta degrees. We also had some carburized iron there at around 35 and then 43 degrees Celsius. Those are the typical conditions for metallic iron and carburized iron. A bit of desulfurization and carburization over there. In all the parameters that we measure, we saw that the plastics far outperformed the conventional material that was used in the industry. If you want the reasons for the improved extent of reduction, I've already mentioned them. The presence of both carbon, hydrogen, and then the thermal decomposition process products of hydrogen gas. They all take part in the reaction, and then they bring about improved chemical reaction. Every ion must pick some carbon so that when you are melting, you need to cut down on the temperature because it's also a way to reduce your energy. We did some carburization, and we saw that when you use only coke, the conventional material, the carburization was slow, but in the presence of the polymer, you had hydrogen reacting to give us a very fast reaction. For this reason, carburization was also better for the polymers. We move on to desulfurization. One element that is not a good candidate in iron and steelmaking technology is sulfur. Another one is phosphorus. Accordingly, anytime you want to produce your metal, you check for your sulfur and then your phosphorus content. We wanted to be sure that when we use our polymer, sulfurization will be better, and truly, when we measure the content of sulfur, the metals that was produced using the polymer was far superior to the conventional way of producing your metal. These are some of the conclusions that we drew from. We also wanted to talk about the flexibility of the process. You don't want a situation where you want to set up a whole technology on a material only to wake up one day to see that after all you don't have enough of the material. For this reason, we tried to test for the flexibility of the process. Now, by flexibility, I mean to find out that can I use the polymer alone? And if I don't have enough polymer, can I also blend with other materials? And more so, most steel makers and most iron producing makers will fight you if you come out with the idea of taking away metallurgical compare and then bringing your new product. A win-win situation was to find out whether I could take a bit of my polymer and then a bit of the traditional material and blend them and then see whether I could get the same results. Prof. Chair, I am happy to announce that the flexibility in this case is extremely high. Not only is our waste plastics able to blend beautifully with the conventional material, it is also able to blend with some of the biomasses that we have in our country. I'll mention a few of the biomasses. We've all seen coconut. In Ghana, if you go to the coastal areas, you have a lot of coconut. We've seen palm kernel shells. Abe, what do we use it for? We blended all this with a polymer, and then we saw that regardless of the blend, you can always use them as a powerful reducing agent. I am happy to announce that I had students, most of them are in Australia now. They were all from areas where there was an iron ore, and then also with their ore, and then carbonaceous materials from their own area. I'm happy to announce that they were all able to produce their metals. Most of them are applying their trades in Australia, US, France. I think the last time I checked, I saw some in Germany as well. Prof Chair, the popularity of this polymer reduction technology has gone beyond the shores of Ghana. I am happy to announce that so far I've had three students, master's students. One of them came from far away Cameroon. He brought their iron ore, the Imbalam iron ore. Another one came from Sierra Leone. He came with the Marampa iron ore. And then a third one, which is very, very important, especially as far as Ghana is concerned, because in that country we have the biggest steel industry in the world, ArcelorMittal, one of the biggest steel industries in the world. He also came with the Mount Gangra and the Mount Tokade iron ores. I'm happy to announce that this technology we were able to use it. They were able to produce their own iron. One of them complained that in his area, a lot of heaps of ties that they are not able to do. The ArcelorMittal, what they do is that they come, take the highest grade, and then leave the lower grade for them. And they have heaps of this waste material available. Based on this technology, we are now able to use available raw materials in your area, and then you are able to produce your metal so that you get rid of the heaps of low-grade iron oxide that is consuming them in their respective countries. They've all finished with their masters, and they are back in their country applying their own trade. One of them is with the Sierra Leonean government. He called me about 3 days ago. He wants to come and register for a PhD in the same area. So it has also gone beyond the shores of Ghana, and my Vice Chancellor is here. We were in Germany about 3 weeks ago. We saw a lady originally from Sierra Leone, married to a German, and as we were talk about heaps of waste confronting them in their country. So then I asked the type of waste, and he said it's iron ore. Then I laughed. Then I told one of your students from your country came, and then we have worked on something that will work. They said they are interested in a collaboration with UMaT. We are waiting for them to come, so that I want to see a day where, with my gray hair and then in my old age, I'll be able to go there and then do something to the glory, also to the glory of UMaT. So we use coconut shell, and once again went through, we got the same results. We have also worked on some 2 iron ores from Nigeria. Their biggest iron ore, the Agbaja iron ore, and then another iron ore from Itakpe, Koji. And they all show beautiful results. If you want to see how the metals look like, you can take a look at the slides. You do your reduction, and then your metal is just there. All you need is a magnetic screwdriver. It will take everything away, and the unreduced material will be left there for anything that you want to do. So it's simple, it's flexible, and then it's fast. I've been able to produce iron, having 99% iron within 2 minutes in a horizontal tube furnace. Then, there is a huge pressure on the iron and steel making technology process. Globally, iron making is one of the largest contributors of carbon dioxide. I'm talking about anthropological carbon dioxide into the atmosphere. And steel makers are faced with huge challenge to cut down on their carbon footprint. The blast furnace alone accounts for over 90% of all iron making processes. And the blast furnace is a huge producer of carbon dioxide. So how do we think about cutting down carbon dioxide in a process that is almost about the highest contributor of carbon dioxide. That is where, once again, the polymer reduction technology will come to play. Prof. Chair, I am happy to announce that when we used the waste polymer, because of the presence of hydrogen in the structure of the waste polymer, the hydrogen was able to do the reduction, and as you know, when hydrogen combines with oxygen, you form water vapor. Water vapor is a greenhouse gas, let me say, but unlike carbon dioxide, your water vapor can condense and fall as rainfall, so that is not a huge problem. So once again, we have a situation where our waste polymer is able to overcome the issue about the carbon dioxide footprint. Work that was published in Iron and Steel Institute of Japan, we did the reduction compared to the conventional way, and then we did some blends. I'm happy to announce that we're able to cut down the carbon dioxide consumption by at least 75%. So this is a technology for the future of iron making. So whether you blend it with coconut shell or with conventional metallurgical coke, there is a unique advantage over there. Now, having done that, then, so these are the iron ores that we have in Ghana. We have the Polymer in the western region, Shani, northern region, through to Atiwa in the eastern region. The last time I checked, the iron ore in Atiwa is a no-go area because I've been told that it is in a forest reserve. It is just about the same, has the same property as the traditional Polymer iron ore. And I know that one day we'll go there because unlike gold processing, iron can be mined sustainably even in a forest reserve if we want to do the right thing. You don't need to go into the water bodies to go and take any iron ore because you can't make profit when you do that. So we can mine our iron ore in the Atiwa region. Prof. Chair, in the year 2021, government of Ghana, under the Geological Survey Authority, discovered the Akokrowa iron ore. And in doing that, we just heard recently that in addition to the iron ore in the Oti region, there is also huge commercial deposits of the critical metal nickel in the area. I think this should be of interest to those of us in the metallurgical and the mining fields. It is a huge thing, and then we need to sit down and revise our notes because we need to go there and to demonstrate to them that UMaT can, we have a technology and then we can assist in the processing of this ore. GEADEC and then GISDEC have been set up. In the year 2018, an intervention I made at the then Ministry of Environment, Science, Technology and Innovation went straight to Professor Frimpong Boateng, then Sector Minister, and I went to talk about iron ore and how we could use waste plastics to process iron ore. I'm sure he didn't know about a lot of the iron ores. I mentioned them to him, and then that, I think, resulted in the setting up of the GISDEC. I don't think people know about this. I've also mentioned that iron ores in the sub-region that we have worked on, if you take a look at the slide, we have worked on all these iron ores, Mbalam from Cameroon, Marampa from Sierra Leone, Mangangra from Liberia, Mantokade from Liberia, Itakwekoji from Nigeria, and Agbaja iron ore also from Nigeria. This is a summary of the work we did on the Shani iron ore. Once again, the results is just about the same. This is the original XRD. We use all these pure plastics from HDP, PPP, whatever it is. Then in generating our carbonaceous material, UMaT has come out with a very simple technology. Under my supervision, we are able to convert the plastics into powder form that can easily be used to produce our iron ore. That is the HDP that you see. So you have your sachet, and you see that we have a simple way of converting our sachet to a pulverized material that can be used for the reduction process. Went through this, we use all these materials. Then we form our pellets. We did our reduction. This is the horizontal tube furnace. That is how it looks like when you look inside, temperatures in excess of 1,600 degrees Celsius. We have found a way to determine the reducibility of any iron ore that you can think of. When you reduce in the open, where you have excess oxygen, and then it works, you know that you can take this iron ore and then you produce your metal from it. So we came out with this open reduction system where we're able to do our reduction, then we produce our metal. And I'm sure this will come as a surprise. The microwave oven. All of us here, I think we have some microwave in our various kitchens. It is not only for producing food. We have been able to engineer the domestic microwave energy for reduction. And if you want to know how, when you have such materials over there, this is how the ore is able to absorb microwave energy. All you need to do is to have the pellets, place them in a crucible, and then just switch on. Just like your microwave will heat your food, this one, we have materials that within 3 minutes can heat up from about room temperature to about 1,270 degrees Celsius within 3 minutes. We utilize this heating property, and then we're able to use it to produce our metal. This is our carbonaceous material. And we tried this on the Sheni and the Takwekoji. Reduction degree up to about 91.24% when we use PET as the reducing agent. Went through this, and then these are the reduction concentration of gases that were produced in each case. And a bit of the metal that we produce. When we tested for this metal using the inductively coupled optical emission spectroscopy, ICP-OES, we were able to get an iron content that ranged from about 95 to about 99%. The rest was only carbon. Again, the superiority of the polymers over waste plastics, over the conventional material is also shown over there. Then we went to the Pudo iron ore. The results are not very different, so let me quickly go through. And the key findings that we've got over there was, if you take a look at this, we used just the microwave. We didn't have the access to the horizontal tube furnace. And this is the metal that we produced. If you can see, we tested for this up to about 97 to 99% metallic iron. We also produce ferrosilicon from the process using the same raw materials. Then finally, we went to the steel making process. This is how the steel making process looks like. We utilize the electric arc furnace approach. In what is a process known as slag foaming. Slag foaming. We have G-Tech come in here to tell us that we should change our foaming to forming. It's not forming, it's foaming. Use waste plastics. They said we should not use the word foaming. I'm sure they didn't understand what is meant by foaming. They thought forming forming slag is not important, but your ability to use it to form, cause the slag to foam. When you do that, you're able to cut down on the energy consumption by about 10%, and that translates into billions of dollars every year. So this is a very important process in iron and steel making technology. So we take steps and we make sure that for every steel making run, you have the slag foaming. Even if it is able to foam for about 5 minutes, you're talking about billions of dollars every year. If you have been to a steel making facility before, when they do their steel making and they want you foam the slag and then you charge your slag, that is what happens over there. Temperatures in excess of 1,600 degrees Celsius. If somebody takes you and they throw you in there, you turn into char and then there will be no trace of you. Because like I said, the human body vaporizes at above 500 degrees Celsius. This is 1,600 degrees Celsius. You will not, you just disappear and there will be no trace of you. Our polymer injection technology, therefore, we decided to also go to the steel making, as I've shown in, this, in the video. Wherever we place the polymer, there was a unique advantage. But then there was a question as to how to get the polymer in there. The conventional way has been shown, but you see that as you approach the electric arc furnace, we have a Y shape. Now, one shape is for the normal coke, and then the other shape, the other out inlet is for your plastic waste. And we use pneumatic carrier hose for blowing the plastics into the furnace and then to bring about. I am also, even though I'm not going to show this here, we are also able to use the waste plastics in addition to being used as a reducing agent in the metals reduction industry. We've used it to produce diesel range of liquid fuel. What I'm saying is a technology that we developed at UMaT. This is, I am able to produce, let me not use, I and my group. I think it's better that way. It sounds nice because I don't work alone. I don't work in vacuum. I work with fellow researchers. We're able to turn our plastic waste into petrol, into diesel, into aviation fuel. Yasisa plastics na etuchene no. Itimi turning say plastics no. We are changing into kerosene, into diesel, into petrol, into aviation fuel. These days, when I go to the eastern region, to some villages, I am happy to announce that I go sometimes to the villages and then the kerosene that I produce from plastic waste, I give it to them, which your friend is saying, coal pot, nadu ayi uchako agum. Na washie agum set kerosene no, you produce from plastic waste in the sachet na yetuchene no. It me the petrol, it me the diesel, it me Eddie produce aviation fuel. Aviation fuel they go plane, issue jet or aviation fuel. Nina it me the plastic waste a year. So anytime we have our plastic waste and then we think of just dumping it anywhere, let's remember that this is a product that can be turned into a very useful material. If you are wondering why we can turn our plastic waste into our aviation fuel, our diesel, our kerosene, or whatever. Globally, of all the crude oil that is produced, 4% of that crude oil is used in producing all the plastic materials that you see. And the plastics na yedi no musuo, yedi bucket, ye bibi agum ne man no. Ye produce plastics na kasa from crude oil. And the crude oil no turning into plastics. And the plastics na a crowd no, it's like having crude oil stored in the solid state. And the plastics in the air, it is said the air to kerosene actually, it is said the air to petrol actually, it is said the air to diesel actually. We have found a technology and then we are able to do the reverse to turn the plastic waste into all these liquid fuels and also to solid fuels as well. Prof. Chair, Ghana, the whole world witnessed the pandemic of COVID. And during the days of COVID, we used nose masks. And in Ghana, every day, assuming around that time, the population of Ghana was about 30 million. If everybody used just one nose mask and then discard it, it meant that every day we were throwing about 30 million nose masks into the environment. We didn't know when COVID was going to disappear. For this reason, I and my team, we sat down and we examined the composition or the constituent of the nose mask. We saw that it was just a blend of various plastic waste. Polypropylene, high-density polyethylene, I think some polystyrene, and then nylon. So we said, well, if this is a mixture of plastic waste, then we think we can do something about it. I'm happy to announce that my group were able to turn all these nose masks also into diesel. And this is a technology. Now, because of the flexibility of the process, I already sent some of my students to the hospital environment. I think one hospital, we talked to them, because it's flexible, you can mix all medical waste. Take all medical waste, your nose mask, your gloves, your surgical. My son, the doctor, is sitting here, so maybe he also understands what I'm saying. We have this technology, and then this is a technology that can place in any hospital. And then, because of the hazardous nature of medical waste, the cleaner will just gather, and then he doesn't need to carry it anywhere. You place a reactor there, and then the cleaner will just dump the plastic waste in the reactor. Just press a button, you turn all the medical waste into liquid fuel that can be used by the medical facility to power its trucks and then simple equipment. We are currently working on that. Before I wind up, Prof. Chair, because of lack of employment, we have, if you go to the Ashanti region and Eastern region where I come from, every day around 2 a.m., we have young men and women in an attempt to eke out a living. All they do is that they go around, gather all the vehicle ties that you can think of. There are many of them. Go to any of the vulcanizing shops, you can get your vehicle ties. They go there, gather all the vehicle ties, sometimes hundreds, thousands of them, put them in a boboya, go deep into the forest. What do they go and do? They burn the vehicle ties deep at night when we are sleeping, around 2 a.m. I can think of the disaster they are causing. They burn them, and then what are they burning them for? Every tie has metal wires in there. So all they do is that they bend the tie, get the wires, and they go and sell. I thought when I read about it, I didn't believe until I traveled to Odumase in the Eastern region, and I saw it myself. They bend, get all the wires, place them in vehicles, move to Tema, and then sell these wires to the steelmaking facilities to make a living. The last time I talked to them, they said they make a lot of profit in doing that. That is okay, except that medically that is a very dangerous thing. If you take a look at the composition of a vehicle tire, it contains two polymers, the polystyrene polymer and then the polybutadiene polymer. Whereas the polybutadiene polymer might not be too much of an issue, the polystyrene butadiene polymer has the benzene ring. And because it has a benzene ring, it is a potential carcinogen. And I hope we understand what this means by if I say carcinogen, anything that can cause cancer. When we were growing up as young men, kids, and then the like, we had the notion that cancer was the disease of the white man. Today, the situation is very different. Cancer is, everywhere in Ghana. It's not only about being civilized, but it's about how we handle our waste. They go, they burn the plastic waste, sit down, inhale all the toxic fumes, get their money. In 5-10 years, they start coughing blood, and then they think that the old lady somewhere is a witch, or they have been, their partners have taken them to some juju to kill them so that they can take over the trade. To solve this problem, we also considered how to use these vehicle ties in a way that we can help the people over there. One, we are not going to stop them from getting their wires to go and sell, but we also want to let them know that they can do this work sustainably to get their the wires and then get something in addition. I am happy to announce that we found a way and we're able to convert the fumes that they were poisoning themselves. We capture the fumes, turn them into diesel char, and then they get their wires. We're looking for funding for this project, and I hope that we're going to get it. Let me mention over here, Prof. Chair, that most often we get questions like, "Namu lectures akura ne research samogana akura adwuma be namu di." And especially when it comes to our book loan, our book and research allowance. I have to talk about this today because very soon I'll be bowing out in the system. We've been asked time and again about what we do with the book and research allowance. If you want to know, today I am giving you an example of what we use our book and research allowance to do. The work I have presented over here is only partially funded. The rest of the fund is from my salary, from that of my kids, my wife, and then also from the research allowance. If GTech is sitting here, I want to tell them that we don't take the research allowance to go and put up only buildings. We use the research allowance to do our research. And that is exactly what you are seeing. So a lot of my research was funded using the research allowance. And I am not the only person doing that in UMaT. If you go to all the universities in Ghana, in UMaT, I know my colleagues also use their book and research allowance to do research. We wanted to use vehicle ties as a raw material in slag foaming. As I've mentioned, we captured some scenes over there, and we did it. This is the results for the conventional material alone. When they use metallurgical coke alone, they hardly get a foamy slag. So you tend to spend a lot of money on energy consumption. We decided to see what will happen if you take part of the metallurgical coke and then you put vehicle tie there to see how it will influence foaming. If you look at the sketch, I have a horizontal line moving from the ordinate at the point 1, if your graph stays below the horizontal line, your foaming is poor. So if you look at the first graph, this is a graph for metallurgical coke alone, which is a conventional material used by the steel industry. You see that they will hardly have any foaming. Then what happened? We replaced part of the coke with 10% vehicle tie. At some point, especially at the beginning, because of the volatile nature of the reaction when you have vehicle ties, we're able to have about 2 minutes of foaming. And trust me, 2 minutes of foaming you can gain more than about 5 billion every year. Just 2 minutes of foaming. By the time we moved from 10% to 20%, what are we seeing? The green graph above the horizontal line is the situation where we have 20%. And we saw that for about 20 minutes, the system was able to undergo continuous foaming, especially up to about 10 minutes, and then it died down. When we went to 25, that is what we got also perpetually above the line. That was 30%. And we measured the rate of the reaction. And then if you take a look at the slide, you notice that when we use metallurgical coke, the rate of reaction was only 15.8. And it increases progressively to 30% ELT when the rate was about 24.5 mole per centimeter square per second. So once again, waste polymers, whether it's a thermoset, whether it's a thermoplastics, whether it's an elastomer, it's a very useful material for iron and steel making technologies, as well as the slag foaming step of the electric arc furnace steel making process. Then finally, we did some work on the Acknowledgments. We traveled to Acknowledgments in the OT region, got some iron ore, and we worked on it. This is the results. These are the iron deposits, or deposits in the OT region. It looks like the OT region is sitting on iron ore, and from what we are hearing this year, not only iron ore, other useful critical materials are there. So I hope that government of Ghana is going to take this serious. It shouldn't be the usual things that we talk about. We talk about it, and then within 2 years, everything has died down. We need to go there and take advantage not only of the iron ore resources, but also of the critical metals, nickel, tantalum, and trust me, wherever you see nickel, you are likely to get cobalt and copper as well. This was the ore. You see, we did an XRF, and then it's a very rich ore. If I could go, the iron oxide could go up to about 81%, and it is predominantly hematite and silica. We use our polymer reduction technology. I've talked about all this. We use vehicle ties as the reducing agent, once again, for the Acknowledgments iron ore. We didn't burn it, we produced fuel. So this is the fuel on the plastic bottle. That's the fuel that we produced. After the fuel, we're able to get our charred material that we use for the reducing agent. And then we also tried it on all the polymers that you can think of, from pure water sachet, PP, and so on, polystyrene. We did all, and the results was amazing. And finally, if you have been to a fitting shop before, you go to the filling station, you want to change your oil. So these are the containers. You produce, every car will use about one of these every 3 months. So heaps of that. I went to a filling station, no, to a mechanic shop in Dankwah here. And I saw that they had this there, I think Dankwah and then Bogos. And just gather, poured kerosene on it, some petrol, set fire to it, and they were sitting, just circling it and inhaling. We have been able to turn these containers also into diesel. I think 2 of my undergrad students were able to do that. And when we use it as a reducing agent, this is the metal that we obtain when we use the vehicle tie as a reducing agent. And this is our iron nugget. What we need to do today, I wish we had this deck over here. We have the biggest steel making company in West Africa, in Ghana, over here. Their method of steel production is through the electric arc furnace steel making process. In that one, you use scrap, but I think these days they blend scrap with high-grade metallic iron. All the iron that you see here, we use waste plastics to produce them. And these are high-grade, premium-grade iron nuggets that we use. HDP, all the plastics that we throw in, that is what we use. And this is a combination of all the plastics that you can see. XLD will tell you have only iron, nothing else, a premium-grade metallic iron. So, now to the final end of my lecture. Government of Ghana has set up GISDEC. So what must GISDEC do? Which route of iron making should we take? Now, based on the work that we have done so far, we have these routes. We have the basic oxygen furnace steel making approach. We have the smelting reduction iron making through, and then combined with the basic oxygen furnace steel making approach. We have the smelting reduction iron making coupled with the electric arc furnace steel making approach. So all these approaches are there, but which of the routes will be better for Ghana or be the most suitable? This is a summary of the routes. Now, based on our local conditions, we have noticed that Ghana's iron ores are low to medium grade. We also realize that conditions favor iron making by the RHF route. For this reason, for the integrated approach that Government of Ghana want to set up, because of which they set up the Integrated Iron and Steel Development Corporation, we suggest a typical rotary half furnace stroke electric arc furnace route to make maximum use of locally available resources as well as clean the environment. We do not want a situation where we set up this company only to go to China to import large amounts of coal. We have all the materials over here, and we need to take advantage of that so that we can all get to the Ghana that we all dream to have. So the Amankwah iron ore is low to medium grade. Coke-free iron and steel making is possible, so we can produce our iron ore without going to make any, getting coke from anywhere. As you said, conditions favor iron making by the RHF route. And for the integrated approach, it is suggested that the rotary half furnace, electric arc furnace route must be utilized to make maximum use of locally available resources as well as clean the environment. Ladies and gentlemen, to benefit Ghana, so that one day Ghana will be the country in the whole world having a steel-making technology based on plastic waste and available raw materials in the sub-region to begin with. Now I profess. Prof. Chair, I profess that all the plastic waste, there are 6 of them. The first one is polyethylene terephthalate. If you take that one, look at the bottom, there is a number 1 there. So plastics number 1 is polyethylene terephthalate. Plastics number 2 is high density polyethylene. Plastics number 3 is polyvinyl chloride, PVC. Plastics number 4 is low density polyethylene. Plastics number 5 is polypropylene. And plastics number 6 is polystyrene and then expanded polystyrene. Now, I profess that we can use 5 of these 6 plastics for the sake of human health. For now, I want us to exclude plastics number 3, that is PVC. For one, we do not have too much PVC in the system. And then 2, PVC, as you can see, has the chlorine atom. Now, anytime you have carbon coming into contact with chlorine at high temperatures, you end up producing furans, dioxins, and polycyclic aromatic hydrocarbons. These are all potential carcinogens. For now, what we do is to use the 5 out of the 6 plastic waste. The last one, if you want to use it, especially if you want to use PVC, we do what we call a dehydrochlorination step, where we convert the PVC to hydrogen chloride gas for the production of hydrochloric acid, also an industrial acid. And then once we are able to produce our HCl, we are able to get our fuel and then char, and this char can be used in the metals production industry. For now, we think that we have a lot of plastics waste, so we can hold on with PVC and use all the other plastics. Prof Chair, I also used, so the plastics that I mentioned, the 6 of them are the, what we call the thermoplastics. I also use thermosetting plastics. And if you want to have an idea about what is meant by thermosetting plastics, I'm talking about the electrical sockets, the TV set, your laptop, the plastics used in making your laptop, your TV, and then the like. If you go to Abu Ghoshi in Accra, it is the most polluted area in West Africa, if not the whole of West Africa. It is because of the way we get the metals out of the electronic waste. They just burn it. They don't understand what is happening. They burn, they inhale all the smoke, get all the toxins into the atmosphere. We have created a dangerous area in Ghana. I profess that we are able to produce simultaneously metals like copper, like gold, like silver, like palladium, name them, and all the important metals that you can think of. We produce them whilst avoiding the toxins that have been produced in Abu Ghoshi. We turn the whole thing into metals and then also liquid fuel once again. I profess that elastomers, like vehicle ties, so the elastomer forms, it comes in between the thermoplastics and then the thermosets. They also contain carbon, at least 80% carbon, and then 7% hydrogen. All important materials for the metals production industry. I profess that that is also a useful raw material for the production of metals, not only metals in the iron making scenario. We've tried it on copper, we've tried it on manganese, and it works. Any metal that has oxygen, you can use waste plastics to produce metals from them. I profess that in the high temperature process where metals are produced from their ore, Ghana does not need to go anywhere. We don't need to go to China. We don't need to go to Nigeria for any coal, for metallurgical coal. We have the raw materials here in our country to produce these materials. I profess also that these waste plastics, they are not only suitable raw materials for the metals industry, they are also suitable raw materials for the production of liquid fuel and then solid fuel as well. They are also used in the production of high temperature sealants. Finally, I call on all stakeholders, particularly government of Ghana. We have the resources, We have the technology, we have the brains. Whatever the white man can do, we can also do. The only thing we haven't tried is to give the universities of Ghana the chance to be able to utilize their research to solve societal problems. And then you may be asking, but have you tried and then you have not been successful? I don't want to talk about this because anytime I talk about that, it gives me some goosebumps. 2023, the first innovation challenge was launched in Ghana. Of the 150, of the 450 contestants, that was pruned down to 50. I'm happy to announce that UMaT alone had about between 6 and 8 of us in the finals. We went as far I want to acknowledge my fellow contestant. One of them is sitting here. My own dean, Professor William Pamibua, was part of the finalists. We were about 8, and finally we got to about 6 in Koforidia. We demonstrated everything, including the work I've shown here. We went there with my diesel samples, everything. All we needed was just $100,000 to set up an industry. We went there from all the universities across Ghana, full of hope. Regrettably, after a due diligence, we heard about nothing. So if you are wondering whether we are not doing enough, we are. Let me take this opportunity to say that in Dankwah here, there is a lady who turns plantain husk into paper carrier bags. She is in Dankwah here. She was one of the final contestants. We have the knowledge. The only thing we haven't been able to do is to set our priority right. And I pray that one day we'll get to a point where we'll be able to sit down and say that we have behaved like the proverbial ostrich for far too long, and that it is time for us to start taking the right step so that we can bring Ghana to the level that we all aspire to see. I want to thank you very much for coming to listen to my inaugural lecture. Thank you.
Shall we please take the closing prayer? Please, we are praying. Gracious and everlasting Father, we are indeed grateful for your care and support for a successful inaugural lecture. We thank you for what you have done, is doing, and is about to do for this university. Help us, O Lord, to continue to grace our generation with richness in arts and science to build our nation great and strong. Bless, O Lord, the work of this university and the efforts of all who have been vested with authority to administer the affairs of it with honesty and diligence. We pray for all dignitaries, alumni present, students, the press, and all those who came to grace this function for a safe journey back home. And now may the Lord bless you and keep you. May the Lord cause his face to shine upon you and be gracious to you. The Lord lift up his countenance upon you and give you peace. May his presence continue to be with us all as we depart from the grounds of this inaugural lecture until we meet again. Amen.
Hello. Thank you so much for gracing this occasion. To our specially invited guests, please join us outside for a photograph session. To the schools invited, please wait behind, we'll attend to you. To the students, UMaT students, kindly go to the foyer for a little snack. Staff, junior and senior staff, please go to seminar room 2. Convocation, please go to seminar room 1. Thank you so much.